everyone, welcome to your second Vodcast for the summer. So topics covered in this video will include atomic theory, mass spectroscopy data, and calculating average atomic mass from that data, naming and formulating, which should be a review. Be sure you have your guided notes and a calculator handy before you begin, and let's go. Okay, let's start with a review of atomic theory. So starting way a long time ago, the basic idea of an atom or an element actually originated from Democritus and Aristotle. So the difference between these two guys was pretty stark. But anyway, over here on the left you see Democritus, and he believed that elements could not be subdivided. Now Aristotle, he was much more popular. He used the scientific method, he did lots of demonstrations, but he believed that the four elements included earth, wind, fire, and water. But we've come a long way since then. John Dalton was one of the first originators of the first atomic theory. He performed a lot of experiments to test and correct his atomic theory. And there were basically four main components of his atomic theory. First, he believed that all elements are comprised of tiny indivisible particles that he called atoms, and that atoms were really truly the simplest form of matter. Atoms of the same element were identical and unique from any other different type of element. Let's see, the third part was atoms of different elements can physically mix together or chemically combine in a bond. But when they do make these bonds, they combine in whole number ratios to form compounds. And chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element, however, can never be changed into atoms of a different element as a result of a chemical reaction. All right, some other scientists after John Dalton came along. One of them was J.J. Thomson. J.J. Thomson realized that Dalton's indivisible atoms did not take into account electrons and nuclear radiation, which was all the rave back in the day. You see, these things called cathode ray tubes were an area of fascination for Mr. Thomson. He actually ended up discovering electrons. Through the use of these cathode ray tubes, he found a particle that was 2,000 times smaller than the smallest atom currently known to exist, which was hydrogen. How could a particle that is 2,000 times smaller than hydrogen exist if hydrogen is the simplest element? So using his cathode ray tube, what he would do is he would fill up a tube, or rather empty a tube, we should say, and create a vacuum. And he would pass an electric current from one end of the tube to the other end of the tube. And lo and behold, he had this beautiful kind of luminescent ray that would extend from one side to the other. And as you can see in this photo, there is a tiny little magnet that is being pushed down towards those luminescent, that luminescent ray that you see in the middle of that tube. And when he put that magnet down, it bent. That means that whatever was inside of that little tube, which there wasn't anything in there, right? It was a vacuum. Whatever those things are, they must have an electrical charge. All right, so I do have a cool video that I do want to show you, but with the technology that I'm using right now, I can't get the video to embed. So what I'm going to do is I'm going to actually put this link that you see right here, right below this vodcast. So if you want to exit out of this video right now, click on the link, watch it, check it out. It's just a really good review of what I just showed you here. So some other scientists came along and discovered other parts of the atom. We credit Goldstein with discovering protons, and we credit Chadwick with discovering neutrons. And these were not easy discoveries to make. But at the time, the prevailing theory was from J.J. Thomson with his cathode ray tube, was this model of an atom, and some models are good and some models are bad, but his model was sometimes called the plum pudding model. It basically was a positive ball of dough with these negatively charged electrons sticking inside of them. So think of it kind of like, I don't know, cookie dough with chocolate chips stuck inside. And the dough is positively charged, and those little chocolate chips are negatively charged. This was the prevailing theory until someone decided to test that theory. And the test that was done is sometimes called the gold foil experiment. And this was done by a gentleman by the name of Rutherford. Oh, he was the student of J.J. Thomson. Haha. So what he did was he pointed a radioactive source of helium nuclei Now, if you look at helium on the atomic or on the periodic table, its atomic number is 2, and it has a mass of 4. That comes from 2 protons and 2 neutrons in the nucleus. Now, if you just have 2 protons and 2 neutrons, protons are positive, neutrons are neutral. These particles had a positive charge. So if you aim that at some atoms that are really, really thin, a really thin sheet of gold, what would you expect to happen if this is what you thought an atom looked like? You've got a positively charged ball of dough, and you're pointing positively charged particles at them? Well, wouldn't you expect them to just kind of bounce off or maybe deflect or pass through, right? But not, they would find tiny little holes to slip through or just bounce back at you. That's what we would expect. I mean, kind of think of me throwing a tiny, tiny tennis ball at, say, like a giant basketball. Yeah, they're going to bounce off, right? So what actually happened was very surprising. So to everyone's surprise, the majority of the particles that he shot at the atoms passed straight through. Now, some were deflected, and a very small portion of them actually bounced back. So the model of the atom had to change, had to account for something that would behave this way. And so Rutherford changed the model of an atom. He said that the atom must be mostly empty space, which is really surprising, and that there must be something really, really, really dense and positively charged in the very center of the atom. Now we know that that is called a nucleus. And the nucleus is very small, and it is very dense. And yes, atoms are mostly empty space. Ah, fascinating. All right, so the new theory suggests that the atom is mostly empty space, explaining the lack of deflection of those alpha particles. He concluded that all the positive charge and most of the mass must be contained in the center of the atom, and that was called a nucleus. So I mentioned James Chadwick too. He did a lot of research that showed that the nucleus of an atom contains more than just protons. Because you see, we figured out that these atoms, they have mass. And the atomic mass of the atom wasn't equaling the charge of the atom, that positive charge of the nucleus on the middle. You see, they were able to take all of these atoms and strip their electrons away and just look at the charge in the nucleus. They realized that the charge and the mass, they didn't really match up. So they had been theorizing and theorizing about this other particle that must exist. And James Chadwick was one to figure it out. So what's fascinating here is that the electrons, they contributed nothing to the atomic weight of the atom, so there must have been another particle that belonged inside of the atom. All right, Bohr's model is commonly used to show the arrangement of electrons around the center of the nucleus. The Bohr model of an atom led to the discovery of the quantum mechanical atom model of electrons. Because you see, electrons, they're not just stuck in these, solid states of rings. We actually we found out that these electrons, they have a very specific amount of energy that they can hold. And that energy corresponds to the orbital that they have. So what evidence do we have for that? You see, we figured out that these electrons, they're, hyper. They're really, really hyper. They have tons of energy, and you can actually give them energy, but they can't hold it for very long, and so they'll release that energy back to you. And these small bits of energy that can be absorbed or emitted, those are called quanta, and that's how we got the word quantum mechanics. That's right, people. I'm teaching you quantum mechanics right now in AP Chemistry. Like, what? So, electrons can absorb energy. And when they do, they will move into those higher energy rings from the Bohr model. But they can't stay there very long, so they usually fall back down into lower energy levels. And when they fall back down, they will emit energy in the form of light. And so what's interesting is that the sun emits all colors of the visible spectrum. And so in this example here in the picture, do you see how it looks like a smooth rainbow? Well, atoms, when they absorb or release energy, it's not a very smooth process because, like I said, there's these chunks of energy that can be absorbed and these very specific chunks of energy that can only be emitted, which helps us to verify the existence of these atomic orbitals, these electron orbitals. So check it out. Each atom ended up spitting out very specific chunks of energy and having very specific, what we like to call spectra. So here's an example of a few elements that I have here. Notice how only certain lines appear? Yeah, remember how the sun was like a smooth rainbow? Well, these elements, they're not smooth. They are chunks, and they are called spectra. This is the evidence that supports the existence of these quantas, these specific pieces of energy that correspond to the electrons' orbitals. So finally, we reach about the 1920s when we finally wrap this whole quantum mechanical model together. And man, have we come a long way. We know that of the existence of s orbitals, p orbitals, d, f orbitals, and those kind of correspond with, I don't know if you are familiar with this, but the s, p, d, and f block of the periodic table. So we will learn much more about this later, but I'm glad that you have just kind of a basic rundown of all the different models of elements here, of the atom, and how far we have come. So the next topic we're going to talk about is mass spectrometers. So suppose someone gives you a bucket full of elements and tells you, hey man, I want you to separate each and every type of atom that you see in this bucket. Well, how could you do that? That's where mass spectrometers come into place. First, what they do is they'll take all of those atoms in your bucket and they will shoot some electrons at them. And when you do that, they actually will turn all of the elements in the bucket into ions. They'll have charges. They'll either be positive or negative. Now, what we'll do then is we'll pass it through a magnetic field, and as they pass through, charges, magnets, they kind of bend. So just like those cathode ray tubes, right? So as they bend, they'll bend a specific amount, and a computer will detect and tally up all the ions of the different parts and give you like a spectrum that you can look at and figure out how many of each one you've got. Sounds kind of complicated, right? Here's some more detail. Check out the picture here. So as a sample is injected in part 1, it will hit a powerful beam of electrons. This is going to ionize the sample. The sample is then run through a powerful electromagnet to speed them up, because remember, they have charge, right? So we're going to make them accelerate in part 3. In part 4, the sample of ions is then shot through a magnetic field. And remember, charged particles, magnetic field, they're going to bend into an arc. The lighter particles and the ones that have a more positive charge, they're going to bend more. And the heavier ones, or the ones that are more negatively charged, they're going to bend a little less. The ions split into a spectrum, which is then printed out on a computer. So what does that look like? Well, it's going to look kind of like this. The picture there on the upper left, that is a real mass spectrometer going on right there. And then, I don't know if you can see this very well, but we do have a printout of an actual spectra that has been created from a machine. Now that spectra over on the lower right-hand side is a sample of molybdenum, and it's an element. So why in this printout do you see 7 clear lines appearing for molybdenum? And you'll notice down on the bottom, they have like different masses. Do you see that? They have the mass charge ratio. That's what that M over Z. M is the mass, Z is the charge. So why are there 7 separate lines? Guys, that corresponds with the 7 isotopes that are known for molybdenum. Cool, right? So why am I teaching you this data, this stuff? Well, this data helps us to calculate average atomic mass. So you'll notice here that I've given you the formula for average atomic mass, just in case you forgot what it is. It's right here. This is the formula for calculating average atomic mass. For each isotope, you have to take its mass and multiply it by its abundance. So abundance is typically given as a percentage. Down here, you'll notice that that abundance is changed into a decimal. So make sure if you are given the percent abundance that you change the percent into a decimal. Just divide by 100, okay? You're going to do this for each and every single isotope that you've got. So here's isotope 1, here's isotope 2, and if there was a third one, you would repeat and keep going. Do that for each and every isotope that they give you in the printout. So you'll be getting a lot more experience with those spectra data in class, but I do want to introduce it here in the video. All right, so let's move on. Let's go back a little bit to Dalton's atomic theory. So there were five key parts of his atomic theory. Number one, elements are made of extremely small, particles that we call atoms. Part two, atoms of a given element are identical in size and mass. That's not true. We know about the existence of isotopes. Isotopes are the same element with a different mass because they have a different number of neutrons but the same number of protons. All right, so keep that in mind. Part three of Dalton's atomic theory said atoms cannot be subdivided, but man, we live in the modern world. We know that we can split atoms, right? So fission and fusion kind of cut that out, so that's not true anymore. Part four, atoms of different elements combine in simple whole number ratios. Absolutely. And in a chemical reaction, we can't like magically change one element to another. All right, and that's still true. All right. So Dalton's atomic theory, just giving you a little recheck here. All right, it's time to go on to our last subject in this vodcast. This should be a review, but as always, I am going to provide you with extra resources and extra links just in case any of this doesn't make sense. You'll find them right underneath the vodcast after I post it, okay? All right, so if any of this doesn't work for you or if any of this doesn't make sense, don't worry, I'm going to give you some extra links just in case you want to check it out. All right, let's take this topic, naming and formula writing. First thing that you need to remember is that we have three different types of compounds that we work with in chemistry. We have ionic compounds, we have molecules, and we have acids. Those are the three different types of compounds that we work with when we're naming and formula writing. So remember, ionic compounds are made with metals and nonmetals, and you have to balance charges. Molecules share electrons, and molecules are made with nonmetals only. All right, acids, they typically have a hydrogen in the front, except for water, right? Water isn't an acid, but it does have a hydrogen in the front of the formula. And I don't know if you knew this, but in acids, you also have to balance their charges because they behave just like ionic compounds. So starting first with ionic compounds. Ionic compounds, you want them to have a neutral charge. You don't want any charge left over. The number of electrons lost by one element has to equal the number of electrons gained by the other. So here's a good example. We have calcium and we have fluorine. Calcium wants to lose 2 electrons to be like argon, and fluorine can only gain 1 electron to be like neon. So this compound has to use 1 calcium and 2 fluorine atoms. All right, it's kind of like calcium is spitting out 2 electrons. So he's able to spit out 1, 2 electrons, but fluorine can only catch 1 at a time. So here's 1 fluorine here, and he's like, I got that one. All right, but he can only catch 1 at a time, so it's going to take 2 fluorines in order to catch both of those electrons that have been spit out or lost. So when you write formulas for ionic compounds, there's some rules that you have to remember. The cation always has to be written first, all right, in the formula. The anion, the negative guy, always has to be written second. So the cation, positive first, negative second. Subscripts, those little numbers that go down low, they represent how many of each ion you've got in the formula. So let's do a quick example. What's a formula for the ionic compound containing magnesium and bromine? All right, so grab a periodic table if you don't have one. Just kind of look at one, please. Take a minute. Magnesium has an atomic number of 12. Which noble gas is the closest noble gas to magnesium? Neon. Okay, now noble gases are on the far right-hand side. And neon has an atomic number of 10. Well, magnesium has an atomic number of 12. That makes magnesium want to lose electrons. Now remember, electrons are negative, so if you lose negatively charged stuff, you become positive. All right, so if he's going to lose 2 electrons, that means that magnesium is going to have a positive 2 charge. Next up, bromine. Bromine wants to be just like the noble gas closest to it, which is krypton. Krypton's atomic number is 36, bromine is 35. So this guy, he needs to gain 1 electron. So he's going to have a negative 1 charge. So let's bring these two together. Magnesium has a positive 2, bromine has a negative 1. You always write the positive element first, negative guy second, and if bromine is able to spit out 2 electrons, right, and bromine is only capable of catching 1 at a time, right, because it wants to have a negative 1 charge. Here's bromine. He caught this guy. you need another one over here to catch the other guy. So the formula is MgBr, and that should be a little 2, that should be a subscript 2. Now, when we talk about naming ionic compounds, you have to recall that cations, they just keep their original name. Anions, as long as they are monatomic, mono means one, atomic means atom, as long as they're monatomic and you've grabbed that ion from the periodic table, we will end its name in an "ide." So ionic compounds are made with cations and then anions, and we write the cation first and the anion second. Well, the same rule applies for when we name them. So a good example would be this guy right here. This is sodium chloride right here. And you're familiar with that, right? Sodium chloride, that's it. So easy. So what would, and I think it's chopped off here, what would the name of this compound be? MgS. Well, the Mg is magnesium, right? And S is sulfur. But you see how you changed this guy's ending to an "ide"? We need to do the same thing here. This would actually be magnesium sulfide. But not all anions are monatomic. Some are polyatomic. And I'm going to give you a good example here. I don't like the way this is written. Let's look at it this way. PO4, and it has a -3 charge, like that. So it has 1 potassium, 4 oxygens, and this whole group of atoms is working together as a group with and has a -3 charge. Whew, that is a polyatomic ion. And polyatomic ions are uniquely named. And lucky for us, I'm going to give you guys a list of polyatomic ions so that you don't have to memorize how to name them. Now, if I gave you that list, you would notice that this particular polyatomic ion is called phosphate. Do you see how it ends in an 8? Well, there's another polyatomic ion that is very similar to phosphate. It's actually phosphite, PO3, with a -3 charge. It's a polyatomic ion. It has 1 phosphorus, 3 oxygens, and it works together with a -3 charge. And its name, again, is phosphite. And here is the general rule of thumb. If you ever seen a name, something that ends in an 8, or something that ends in an ite, 8s and ites are polyatomic. Well, usually. You will get a much more detailed list on the first day of school. So if I were you, I wouldn't concern yourself with this much. If you need any assistance though, I'm sure you can Google it or search it up on the internet, and I guarantee you'll be able to find whatever you're looking for when it comes to naming and formula writing for polyatomic ions. Alright, some rules when you're using these polyatomic ions are pretty important. In a formula, when you use a polyatomic ion, you have to check to see if you need more than one. If you need more than one polyatomic ion in a formula, you have to put the formula of the polyatomic ion in parentheses with a subscript on the outside. Here's a really good example. Let's look at magnesium chlorate. So first, figure out the charge of your magnesium. We already did that as an example. And then figure out what the formula and charge of chlorate is. You see how it ends in an 8? So you know it's polyatomic. So magnesium, we know, has a +2 charge. Chlorate looks like this. Chlorine, oxygen, 3 of those oxygens, and then this group, it has 4 atoms. It has a -1 charge. So you have a +2 and a -1. You always write the positive guy first, so we're going to do magnesium first. We're going to do chlorate second. And you'll notice that we need more than one chlorate. So what we're going to do is we're going to wrap that guy in parentheses. See how I wrap the entire polyatomic ion in parentheses. And then I place a 2 on the outside just like that. And there's your formula. That's magnesium chlorate. Here are some other ones that I'd like you to try. Now, if you get stuck, please remember to try to look this up yourself and try to learn how to do these yourself. Let's move on. You will be expected to understand these prefixes all the way down to deca. The reason why is because we are going to have to use these when we name molecules. There are 3 rules for naming molecules. The first atom in the formula only gets the prefix, these prefixes right here. It only gets a prefix if there's more than one in the formula. But the second atom always gets a prefix, even if there's only one. Remember, the prefix for one is mono. And the second atom in the name must end in an "ide." All right, if you're wondering what that squeaking is in the background, I have pet guinea pigs, and they're kind of being annoying. Do you guys want to see them? Hold on. All right, you guys, check this out. Say hi, guinea pigs. Ginger, Ginger, Pepper. That's their names, Ginger and Pepper. Hi, guys. What are you doing? What are you doing? Be quiet, I'm trying to make a video. Shh, be quiet. Sorry, guys, I thought that was pretty cute, though. All right, so I've got some examples here. We got carbon dioxide, dihydrogen monoxide, phosphorus tetrafluoride, and disulfur hexaoxide. Why don't we try some of these down below together? So in that first example, you've got phosphorus, but you only have one of them. So you would simply write his name out. Phosphorus. All right, because the first element only gets a prefix if there's more than one. But the second one always gets a prefix, and you see how there's 6? So that would be hexa. Hexa is 6. Now hexa, and that's chlorine, but we're going to say chlor. That's right, chloride, because you got to remember to do the ide. So you see the prefixes here and the suffixes. All right, you try the other two alone. I'm sure you can do it. It's not that hard. Let's keep going though. There's only one type of compound left to learn, and that is acids. Now, when we name or write the formula of an acid, everything is determined by the name of the ion used to make the acid. Remember how I told you got to balance charges of acids? So here's the general rule. I know it doesn't make sense very much, but let me show you how to use this, okay? Here's an example. Hydrochloric acid. So in this particular example, you have a prefix of hydro, you have an ic, and of course we call it the acid. So because you have this prefix hydro in the front and ic at the end, this particular acid must have come from an ion that ends in ide. Now here's the part where you have to rely on some of the stuff I've been telling you. Any ion that ends in ide came as a monatomic ion from the periodic table. Now there's a couple exceptions, but don't worry about that until later. So the acid itself must have come from the ion chloride. Now chloride should sound familiar to you. That's chlorine, right? Now chlorine, you find it on the periodic table. It is really close to another noble gas. That is going to give it a -1 charge. It has a -1 charge. So what we're going to do is we're going to put those hydrogen ions in the front. Remember how acids have a hydrogen in the front? Hydrogens have a +1 charge. So the formula for hydrochloric acid, you put the hydrogen in the front, you put the chlorine in the back, the H is +1, the chlorine is -1, voila, you're done. All right, guys, let's get some practice now. So in this first example, what I like to do is I kind of ignore those hydrogens that are in front, and I look at whatever's left. I've got a PO4. Now, if you don't have a list of these polyatomic ions, you just look up on the list what is the name of PO4 ion. And the name of this ion is phosphate. That's his name. So you look up the rule for naming acids when you have an 8 ion, and it'll tell you that you need to switch the 8 to an ic. So a lot of people like to say that the name of this is phosphic, but I don't know if you knew this, but there's a special rule for phosphorus and sulfur. You see, phosphorus and sulfur, they have that sound in their name. Phosphor, sulfur. And instead of calling it phosphic acid, we actually call it phosphoric acid. So try to remember to keep that sound in there. In the next one, ignore that hydrogen. This is called bromide, right? It's bromine, but we call it bromide because we grabbed that ion from the periodic table. So anytime you have an ide ion, you have to put that hydro in the front. Then you're going to say brom and change the ending to an ic. So you see how you have the hydro in the front and the ic at the end, and we'll call it an acid. In the next one, ignore those hydrogens. Who is SO3? You'd have to look that up, but I'm going to help you out right here. This is sulfite. This is the sulfite ion. So you see how it ends in an ite? The rule for that is that you have to put an us, O-U-S at the end. But do you remember when I told you above about the phosphorus and sulfur? What do you have to keep? What do you have to keep in the name? You have to keep the in there. So a lot of people would actually call this sulfus acid, and that's... All right, guys, that's pretty much it. Here are a couple little reminders about naming and formula writing. For ionic compounds, it's always a metal and a non-metal. You have to balance charges. And as we start learning all these rules, you have to remember that ionic compounds won't have prefixes in their name. No mono, di, or tri. Ever. Ever, 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 ever. Covalent compounds, those are the ones that are sometimes called molecules, and they're only made with non-metals. You do not balance the charges, but this is the only one where you have to use prefixes, mono, di, tri, tetra. Only one. Acids. Acids have the hydrogen in the front except for water. You do have to balance your charges just like ionic compounds. And remember the 3 rules for your names. Remember, none of those rules talk about prefixes like mono, di, tri. So get rid of those. The only time you use prefixes is in molecules. Ladies and gentlemen, I am looking so forward to our first day of class together, and I can't wait to meet all of you guys. I hope these videos have helped, and as always, if you have questions, don't be afraid to ask me, okay? I'll be here whenever you need me, and you can always email me over the summer, okay? And like I said, don't panic if you don't finish your summer assignments or your Vodcast and guided notes. You will have time to complete those, okay? All right, you guys, I'm looking forward to meeting all of you. Talk to you later. Ciao.